Okay, let's look at a design example where instead of checking an existing selection, you have to actually pick one yourself. So our first thing, it says select an ASTM 992 W shape with an 8-inch nominal depth. So we're talking about a W8, right? That means a W8. An ASTM 992. Go to your page 2-48, which I hope you have tabbed. And A992 at the bottom has an FY of 50 and an FU of 65. Right? So I want to select a W8, A992, FY is 50 KSI, and FU is 65. Right? FY is the yield stress, FU is my stress associated with rupture. And I need it to carry a dead load of 30 kips and a live load of 90 kips, and it's 25 feet long. We're gonna ignore the ASD. We're just gonna use LRFD. And we've got to assume that the connection limit states do not govern, so we're gonna ignore block shear. So first, calculate our required strength, our factored load. So PU is 1.2 dead plus 1.6 live. PU is 1.2 times 30 kips, that's my dead load, plus 1.6 times 90 kips, which is my live load, and that gives me I need something that will carry 180 kips. Okay, so now I'm gonna go to my tension section in the manual. So the tables at the beginning in the first, 2/3 of the book, part 5. And I'm going to look at these tables to pick a section. I did have that. Oh, it's not there. So, I don't know, let's see, page 400 table. A lot of tables. Oh, that's down in flexure. So, I'm gonna go look at my tables of available strength and tension, right? Table 5-1 is my W shapes. And you can see it lists the W shape, and then also remember we need to make sure and check that this has the same material properties of the steel that we're using. So we're using A992, which has an FY of 50 KSI and an FU of 65. So these tables are valid. So I need to go find the W8 section. Let's see, right? It kind of tells you can see in the corner. W8, so in the 15th edition, this is page 5-13, and I need to find something that'll carry 180 kips. So I go and look, and be sure and stay in the LRFD. Not the green columns, the white columns with blue writing. Because we're in LRFD, not ASD. So I need a W8, I'm in the W8 section, and I need one that will hold 180 kips. And let's see, the smallest one, it looks like, is a W8 by 18. Everybody see that? So I'm on page 5-13. It'll look a little bit different in the 15th edition, but you scroll down and it should say a W8 by 18 is 237 kips yielding and 193 rupture. So I'm going to W8 W8 by 18 has a yielding design strength of 237 kips. And 193 kips rupture. Right? So, now if you recall, let's go back and look. There are two big assumptions in these tables. Does it say in them? No, it says it in the commentary at the beginning of the part. Design table discussion. It's assumed that your effective area is 0.75 AG, your gross, 75% of your gross cross-sectional area. When your effective area is greater than that, then your rupture rate, when your actual effective area is greater than that assumption, then you know that you'll be fine in rupture because you actually even have more than the table thinks you have. But if you have less than 0.75 AG, then the tensile strength can't be used and you actually have to calculate it. So the biggest assumptions in these tables are the material properties and then this effective area versus gross area relationship. So that means that actually this yielding is fine, right? I can go look up a W8 by 18, which we just had, and if I use the yielding, which we can use it just to check it, but right, it's going to be valid, right? 8 by 18. Let's see, a gross cross-sectional area of 5.26 and 75% of that is 3.95. So I selected my section, and I'm going to verify that it's actually going to work. So check well, what did I actually say? Right. Check design strength, right? So we'll write it just for fun, but yielding. If I go to chapter D, I can see, page 16.1-28, yielding, or you can look back on in these notes. VT, my fee doesn't need a tail. VT-PN is phi T AG FY, and so that's 0.9 for yielding. Remember, it's different for yielding and rupture. 0.9 for yielding. My gross cross-sectional area, I just looked it up. It gives it to me 5.26. And you could also look it up. You could also look it up in the dimension tables in the beginning, the part 1. Let me check this up. 5.26 inches squared. My FY is 50 KSI. So for yielding, I get a value of 237 kips, which is what the table said. Right? The table's not lying, right? The table actually uses these equations that they say they use. So matches table, right? And that is greater than our required strength of 180 kips. So, okay, yielding is fine. Now comes the part of my rupture. I have to calculate my net area, my shear lag factor, my effective net area, and compare it to that 0.75. And if it's less than that, I have to use that number, and it will, to calculate my actual rupture limit state design strength. So just to remind ourselves, for rupture, AEFU. So let's go and look at my cross section. 3/4 inch diameter bolts in standard holes. So my diameter of my bolts is 3/4 inch. If I go look at my table J3.3 on page 16.1-130, my diameter of my bolt hole is, for a 3/4 inch standard bolt, is 13/16 inch. My net area is going to be my gross cross-sectional area minus 3, 4. I have 4 bolt holes. Number of bolts times my diameter of my bolt hole plus 1/16 of an inch. That's my 1/16 of an inch accounting for damage times the thickness of the flange, because the bolt holes are in the flange of the W section. So I need to go look up what that is. So you flip to let's see, page 1-28. Let's see. 8 by 18 has a gross cross-sectional area of 5.26. And I wonder if I should use the highlighter. That might be nice. Let's see. 5.26 and a flange thickness of 0.330. So my net cross-sectional area is 5.26 inches squared minus my number of bolts is 4. My bolt hole is 13/16 of an inch plus my 1/16 and 0.330 inches. So net is 4.11 inches squared. Now I need to figure out how much of that net area is effective. So I need to do my shear lag factor. If I go to chapter D, I look at my shear lag table 16, page 16.1-30. This is a, let's see, what page would that even be on? There we go. So it's either case 2 or I might be able to use case 7. Right? If I have a flange with 3 or more fasteners in the direction of loading. So let's see if I can use that, because then I don't have to do more math, but we'll check both just in case. So can I use it? Flange with 3 or more fasteners in the direction of loading. 1, 2, 3, 4. All right, I can use case 7. So I'm going to do case 2 and case 7. to make sure that I have the most accurate one I can use. So let's see. Case 2, I need, if you go back and look at that drawing, I actually need to find this, well, it's this, but I need to use a WT section to do it. Because this, when you're connected with the flanges, it's basically like two WTs that just happen to meet in the middle in the stem. So I need to find this eccentricity using a WT section. So I need to look at a WT. This is an 8 by 18, 4 by 9, right? WT 4 by 9, half of a W 8 by 18. And if I go look at that, it will help me find that eccentricity. Let's see. Okay, I'm in my WTs. I need to go scroll down and find the 4 by 9. See, WT 4 by 9. Oh, on the next page. 4 by 9 has, alright, WT 4 by 9. I need actually to go to the next page. I need to look at the Y bar. Right, if you look at this image right here, I need this dimension. So I'm actually looking at a Y bar. Right, if you compare that to what you're looking for in the shear lag table, that's what it looks like. So even though it says X bar is just for the eccentricity. It means eccentricity, but it could be a Y bar as the actual symbol. So I need to know the Y bar for a 4 by 9. Here it is, 0.834. Right, if you are on page, let's see, page 1-73 in the manual, yep, 0.834. Oops. And my length of my connection is 3 times 3 inches. So it's 9 inches. So U equals 1 minus x bar over L is 1 minus 0.834 inches over 9 inches. 1 minus 0.834 divided by 9, 0.907. I can also use K7. K7 is where I have three or more fasteners in a row. Let me just make sure that that's the same thing. Flange connected with 3 or more fasteners in a row. If my flange width, that's what BF is, it's my flange width, is greater than 2/3 of my depth, I can use 0.9 or I can use 0.85. Now this will actually end up either being 0.9 or 0.85, but it doesn't matter because I got 0.9 using case 2, but we'll still calculate it just for practice. So let's see, I need to know for a W 8x18, the flange width and the depth. So let's see. It's like 8x18. My depth is 8.14, right? W 8x18, 8.14. Maybe I'll blow that up a little bit. 8x18, 8.14, right? It's about 8 inches, right? It's nominally 8, but, and then my width of my flange is 5¼ inches. So I need to do my BF compared to 2/3 of my depth, where my width was 5.25 and 2/3 of my depth, which was 8.14. So that is 5.42. So my flange is less than that. My flange width, and it says if it's less, then I can use a U of 0.85. So everybody see how we did that? I went to my shear lag and it said I can use case 7 or case 2. Case 2 is the generic, and 7 is I have a W shape with 3 fasteners or more in a line in the direction of loading. I actually have 4. So I can use this case 7. I compared my flange width to 2/3 of the depth, and it ended up being less. So if I wanted to not do the calculation, or if maybe the 1 minus X bar over L gave me a lower number than 0.85, I could use this. So, but it actually ends up not mattering, but, so U equals 0.85. I get to use a larger value. It's like the one time in your life you're actually allowed to use a larger value, right? So now I can calculate my effective area. That's what all this was, right? My effective area, AE equals UAN, right? My shear lag factor times my net area is 0.907 times 4.11 inches squared. That's from up here. So 0.907 times 4.11, 3.73 inches squared. How does my effective area compare to my gross area? .73 inches squared. My gross area was 5.26. .709. That means therefore my table assumed that it was going to be 0.75 or greater, and it's 0.709. So that value that I had from the table, which was 0.93, is no longer correct. So I need to actually calculate it. How did that work a second ago? It didn't work now. Interesting. So my rupture, I can actually calculate it. Phi T PN is my phi for rupture times my effective area times my ultimate tensile strength, which the phi for rupture is 0.75. My effective net area is 3.73 inches squared. And my ultimate tensile stress for A992 steel is 65 psi. Right, that's all the way back. Right there. So for rupture, my tensile strength is I hope that's right. actually greater than my 180, so that's good. That is greater than my required strength. So, alright, my W 8 by 18 actually works. It just barely, but what you'll also notice is with the configuration, with the geometry, my rupture limit state right? Yielding was 237 and my rupture limit state was 182. Actually, without that, it was going to be 193, right? But it works. So my last thing that they wanted me to do was check let's check our slenderness. So according to D1, we want our L over R to be less than 300. My R, if I go and look for a W 8 by 18, CW 8 by 18. My radius of gyration, 8 by 18, right? Yeah, 8 by 18. Radius of gyration 3.43 or 1.23. We're going to choose the 1.23. We're going to choose the lower value because that'll give us a higher slenderness ratio, right? Eight by 18, 3.43, 1.23. My length is 25 feet. Okay, 25 feet. Oops. $25 long. And my RY is 1.23 inches. So L over R is 25 feet times 12 inches per foot. 0.23 inches is 244, which is less than 300. So it's good there. So I can choose the ultimate at the end of the day. W8 by 18. I figured out that it works for yielding, it works for rupture in the current configuration, which you always have to check because it might be different than that 0.75 assumption. And then I check my slenderness, W8 by 18. Okay, and that is how you pick your own section. Now, if I had gone and this hadn't been just over 180, I would have had to have selected probably the next largest section, unless it was really off, but would have selected the next largest section and gone through the same process. So design is try something, check it. If it doesn't work, try something else, right? Until you meet all the criteria of your limit states and your slenderness. So that is that example of actually picking a section. Thanks.